Dear students, this is a summary of the topics which we have covered during the last two live sessions on abstract algebra. On the set of integers, we have defined the relation congruence modulo n. A congruent to B mod n if and only if a minus b is a multiple of n. Considering all the elements which are related to each other in one class, there will be n distinct congruence classes. The set of all congruence classes under the relation congruence modulo n is denoted by Zn. Similar to the addition and multiplication of real numbers, we can define addition and multiplication of congruence classes. Also, we have seen that this addition and multiplication satisfy the axioms of real numbers, that is, commutative property, associative property, existence of identity, existence of inverse, and the distributive property combining both addition and multiplication. Also, we have seen that there are certain laws which are not satisfied by the addition and multiplication of the congruence classes. That is, the cancellation law. Here, if it is usual multiplication in the case of real numbers, a dot b equal to a dot c implies b equal to c. But in the case of multiplication of congruence classes, a dot b equal to a dot c does not imply b equal to c. Here is an example. Class of 6 multiplied with class of 5 is the class of 30, and that is same as the class of 6 when we consider Z8. And that is same as the product of class of 6 and class of 1. Here we cannot cancel the class 6 from both sides, and it does not follow that class of 5 equal to class of 1. Actually, they are two non-zero classes which are distinct. We have seen that product of two non-zero real numbers is always a non-zero real number. But in the case of congruence classes, product of two non-zero classes may be zero class in Zn. So here is an example. Class of 6 multiplied with class of 4 gives class of 24, which is equivalent to the class of 0 since it is in Z8. Then we can define the divisors of 0. Two non-zero congruence classes are said to be divisors of 0 if their product is the 0 class. Here is the example. Class of 6 multiplied with class of 4 gives the class of 0 in Z8. Therefore, the class of 6 and class of 4 are 0 divisors in Z8. Multiplicative inverse. If the product of two non-zero classes gives the class of 1 in Zn, then we say that each of the class in the product is invertible. And the inverse of A here, inverse of the class A here will be the class of B, and the inverse of class B is the class of A. And the multiplicative inverse of class A is denoted by class A power minus 1. In set 7, we can find all the multiplicative inverses. We have seen that class of 2 multiplied with class of 4 is class of 1. Therefore, class of 2 and class of 4 are multiplicative inverses of each other. Similarly, the multiplicative inverse of class of 1 is same as class of 1. Similarly, class of 6 multiply with itself gives the class of 1. So, class 6 also has the multiplicative inverse class 6 itself. Then the proposition, let n be a positive integer. The congruence class of A has a multiplicative inverse in Zn if and only if GCD of A and n equal to 1. And the statement B says that a non-zero element of Zn either has a multiplicative inverse or is a divisor of 0. So we have proved this during the live sessions. As a corollary to the proposition, we have seen that if P is a prime number, then set P has no divisors of 0 except the 0 class. Also, the statement is equivalent to the fact that every non-zero element of Zn has a multiplicative inverse. So, all these three statements are equivalent. So, the result easily follows from the previous proposition. Consider the example of set 16. The positive integers relatively prime to 16 are 1, 3, 5, 7, 9, 11, 13 and 15. So congruence classes of all these elements will be having multiplicative inverses in set 16. നമ്മൾ പറഞ്ഞു നേരത്തെയുള്ള പ്രൊപ്പോസിഷൻ സെഡ് എന്നിൽ മൾട്ടിപ്ലിക്കേറ്റീവ് ഇൻവേഴ്സ് ഉള്ള എലമെന്റ്സ് precisely will be of those numbers which are relatively prime to n. അതാണ് ഇവിടെ ഒന്നാമത് എഴുതിയിരിക്കുന്നത്. When we consider the remaining numbers, class of 2, class of 4, etc., class of 14, all these numbers 2, 4, 6, etc. are not relatively prime to 16. So they are 0 divisors in set 16. Then we have defined Euler's phi function. Euler's phi function denoted by phi of n is the number of positive integers less than or equal to n which are relatively prime to n. We can see that phi of 8 equal to 4. The numbers less than or equal to 8 and prime to 8 are 1, 3, 5 and 7. Similarly, when we consider 7, all the numbers 1, 2, 3, 4, 5, 6 are relatively prime to 7 since 7 is a prime number. Therefore, phi of 7 is 6. In general, we can write phi of p equal to p minus 1 if p is a prime number. Now, this is a proposition which we have studied during the first semester BSc course. Then, that is, if the prime factorization of n is p1 raised to alpha 1, p2 raised to alpha 2, etc., pk raised to alpha k, where alpha I greater than 0, then phi of n equal to n multiplied with 1 minus 1 by p1, 1 minus 1 by p2, etc., 1 minus 1 by pk. So we have done examples also to evaluate phi of certain numbers. Then the set of all units of Zn, that means the set of all congruence classes having multiplicative inverse in Zn, is denoted by this symbol Zn cross. So the Zn cross will be the collection of all the units. Units mean those congruence classes which are having multiplicative inverses. So here in the case of Z8, it will be class of 1, class of 3, class of 5 and class of 7. And we have the proposition, the set Zn cross of all units of Zn is closed under multiplication. That is, if we consider two units in Zn, the product of the elements will be again a unit. That is, it will be again having a multiplicative inverse. Now, this is the Euler's theorem. If a and n are relatively prime to each other, then a power phi of n is congruent to 1 mod n. Now, to prove that, we consider r1, r2, etc. are phi of n as the positive integers less than n and prime to n. Then we consider the products AR1, AR2, etc. AR phi of n. Since a and n are relatively prime, each of these integers also will be relatively prime to n. Also, these integers will leave distinct remainders when they are divided with the n. That we can see For if ARI and ARJ leave the same remainder when divided with n, then ARI will be congruent to ARJ mod n. That means n will be dividing ARI minus ARJ. That is n divides A. That is n divides A into Ri minus Rj. So n is relatively prime to A, therefore n divides Ri minus Rj. But it is a contradiction since Ri and Rj are positive integers less than n and prime to n. Each of this AA1, AA2, etc. AA phi n will be congruent to one of A1, A2, etc. A phi of n. Now taking the product of phi of n congruence relations, we get the product on this left hand side congruent to A1, A2, etc. A phi of n in some order. So it can be rewritten in the form a raised to phi of n multiplied with a1, a2, etc. a phi of n equal to a1, a2, etc. a phi of n. The product of this phi of n numbers are common in both sides. We can cancel them. Then what we obtain is a raised to phi of n is congruent to 1 mod n. Hence the Euler's theorem is proved. Using the Euler's theorem, we can prove the Fermat's Little theorem. Let P be a prime and A be any integer such that P does not divide A. Then A raised to P minus 1 is congruent to 1 mod P. It directly follows from the Euler's theorem. If A and N are relatively prime to each other, then A raised to phi of n is congruent to 1 mod n. That is the Euler's theorem. If n is a prime number P, then phi of P equal to P minus 1. So replacing phi of P with P minus 1, we get the result A raised to P minus 1 is congruent to 1 mod P. Now the next theorem, let P be Now the next theorem, let P be a prime and A be any positive integer. Then A raised to P is congruent to A mod P. Now to prove the theorem, we consider two cases. Let P does not divide A. Then P and A are relatively prime. And by Fermat's Little theorem, we get A raised to P minus 1 is congruent to 1 mod P. Multiplying with A on both sides, we get A power P is congruent to A mod P. In the case 2, let P divides A. Then P divides A raised to P also. Then P divides the difference A raised to P minus A. That implies A raised to P is congruent to A mod P. So in both of the two cases, we have proved the result. This is the set of problems for the first assignment. How to prepare addition and multiplication table for the following sets. And also, if P is a prime number, then show that class of A and class of 1 are only idempotent element in set P. An element or a congruence class is said to be idempotent if its square is the element itself. That is, a congruence class square is same as the class itself. Then that class is said to be an idempotent element in set P. So in set P, there will be only two idempotent elements. And the question number 4, 5, all of them you have to do yourself. You can ask if there is any doubt. Okay, thank you.